see. Okay. Hi, everyone. We're great to have Nupur today. Nupur is a postdoc at Dr. Sanjay Banerjee's lab at UT, and her research is in the field of nanoelectronics with a focus on simulations and modeling of devices, device physics, and their application. Currently, she's working in DFT calculations, studying 2D systems such as TMD, transition metal diconide field effect transistors. Prior to that, she worked on semi-classical Monte Carlo modeling of FETs. She received her PhD degree from Department of Electrical Engineering at Indian Institute of Technology, Indore, India in 2018. And before pursuing her PhD, she worked as an assistant professor at Manipal University, Jaipur, from 2013 to 2014, and completed her master's degree in VLSI design from Malavia National Institute of Technology, Jaipur, India in 2013. So we're happy to have you here, Nupur. Be nice to learn more about what you do, and then maybe your journey as you came all the way from India and have change of hats, looks like a little bit. So welcome, Nupur.
Thank you, Suyog, for the introduction. So I'll just share my screen and can start with the presentation. Please feel free to interrupt me whenever you have some questions, doubts. Just give me a second. So, hi, good evening, everyone. So today I'm going to talk about beyond CMOS scaling. Before I go into my research work or something, let me give you a brief introduction about myself. So I have done my, so I am born and brought up in India. I have done my bachelor in engineering in the field of electronics and telecommunication from IIT Indore. So talking about Indore, Indore is basically my hometown. It's a city that's famous for a few historical places and quite a lot for street food. Nowadays, it's being recognized as the cleanest city in India. After pursuing my bachelor's, I did my master's from MNIT Jaipur. So Jaipur is a very beautiful place. It has magnificent palaces, forts, and it's a very colorful city. I had a great time there, staying at hostel, and it was just awesome. I did my master's in VLSI design, and my thesis focused on doing an analytical modeling of SRAM and its peripheral for estimating its leakage current. After that, I joined Manipal University as assistant professor. So teaching there, I realized that I have interest in studying further, doing research, taking up projects with students. And soon after completing an year of my teaching, I joined IIT Indore as PhD. So this is my research group. It's low power nanoelectronics research group. My research area focuses on assessing the performance of tunnel FET transistor for capacitorless dynamic memory. So in PhD, I had opportunity to present my work and to visit various other countries, which was really nice from the point of view of having a wider perspective. And now coming back to my research. So the intent of my work was to design tunnel FET and also understand the physical phenomena happening in tunnel FETs so that it can function as a dynamic memory. Before coming to that, let me give a brief background. So let's talk about device performance. Now for device performance, the three main parameters that are important are its area, power, and speed. Miniaturization of device is really important in electronic industry, and The era of scaling began from Moore's law that states that the number of transistors on a microchip doubles every 2 years. Following Moore's law, there came MOSFET scaling that was being given by Dennard. According to Dennard's MOSFET scaling, the speed of the device increased and the power consumed decreased with the device dimension scaling. Although we have Moore's law still into existence and is shown that it will end by 2025, Dennard's scaling ended very quickly around 2006 itself. So there was a need to have newer devices, architectures, and material. And so the intent of my talk will be to talk about this emerging devices, and that's how my research focuses on. So before that, let's understand that what were the scaling issues. So just a brief. So as we scale down the length of the devices, we also scale down the voltage of the devices. As the power voltage scales down, the on current decreases, and this decrease in on current reduces the speed of the device that degrades device performance. Although we can maintain this on current by also reducing the threshold voltage that controls the ion, which is directly proportional to VDD minus VTH. However, reducing this threshold voltage, our off current increases. Increase in off current affects our static power dissipation. So there is a trade-off between ion and I-off, or trade-off between the speed and the power. So we required few devices that could maintain the speed, had low power, and also showed a higher density. There came the role play of steep switching devices. And they are being characterized by a parameter known as subthreshold slope, which defines the ratio of on-off to switching capability. Now for MOSFET, the subthreshold slope is limited to 60 millivolt per decade. The lower the subthreshold slope, the better device performance is in terms of speed and also power. So there was a need to have devices that can give us a subthreshold slope lower than 60 millivolt per decade. And thus tunnel FET effect transistor were invented. Now when compared with MOSFET, these devices show a lower off current, shows reduced short channel effects, and has a weak temperature dependency, although it shows a low on current. But when we compare the voltage required in case of tunnel FET, if we see in figure 2, is very low as compared to the ideal MOSFET for reaching the same ion by I-off. So we could break this Boltzmann barrier of 60 millivolt per decade by use of tunnel FET transistors. Just talking about how do this transistor operate. So these devices are a PIN devices and operate in reverse bias. This is an N-type tunnel FET. When you apply a gate bias of a gate and a drain bias, which is positive, we could see that the energy barriers or the energy bands towards the channel region and the drain region lowers. It lowers in such a way that the electrons from the source region of the valence band could tunnel towards the channel region. And that's how tunnel FET transistors work. So the condition for its working is that the valence band of source region and the channel region and the conduction band of channel region lie adjacent to each other. Now moving next upon how this transistor were being realized. Now if we talk about applications in the semiconductor industry, they are being categorized into analog, logic, memory, and discrete functionality. Now, tunnel FET has been explored as steep switching devices, logic circuits, and log circuits, but still there was a need to exploit it as memory. So my work focuses on dynamic memory using tunnel FET devices. Now, dynamic memories are fast and dense memories, and conventionally they have been utilized as main memory. However, as we are moving towards more data-intensive application and smart products, the need is to improve the performance of dynamic memories in terms of speed, power, its retention, everything. So next we'll focus how can we scale down the DRAM. That was done through use of a capacitorless dynamic memory. So first thing is, why do we need to scale down dynamic memories? The requirement was to bridge down the gap between the processor and DRAM. So if we talk about processors, the processors have been scaling down from a long time, and their performance have been improved in terms of speed and power. But when we are talking about memory, the memory first intention was just to have it cost effective. So there was a barrier and a gap between processor and dynamic memory. So there was a need even to scale down this memory. Now, if we talk about conventional dynamic memory, it consists of one transistor and a capacitor, where transistor is used as a switch and capacitor is used as charge storage. Now, to scale down dynamic memory, it's essential to scale down its capacitor, but this was a limitation in 1T, 1C. So there came a capacitorless dynamic memory. This is a single transistor-based dynamic memory in which the transistor itself is used to store the charges. And this was possible through use of MOS transistor. But we require tunnel FET devices to show even a lower power consumption in terms of DRAM. So how can we operate tunnel FET as dynamic memory? When we talk about conventional MOS having an NPN configuration, we can see that its P-type well can serve as a potential well where we can store the charges. While in case of tunnel FET, which is a P plus I N plus region, there is no well formation. So we require device architecture so that we can store charges in tunnel FET. So just giving a brief flowchart of how we can operate tunnel FET as a DRAM is, first we need to do is we need to optimize the design of the tunnel FET. That is, we need to create a potential or a storage region in this device so that we can store the charges. Once we have achieved the storage of charges, we need to see its performance in terms of various factors. The first important factor is it should be able to distinguish between state 1 as well as state 0. So we focus upon sense margin, retention time, and then comes the other performance matrices that focuses on scalability, power, and speed. So let's begin with how can this tunnel FET operate as dynamic memory. So this is one of the architecture that was being proposed by me. And this is, in this architecture, we can observe and we have a corresponding band energy to this architecture. The whole concentration under this gate 2 is around 10 to the power 17. This is the condition when you have no bias. Now to write state 1, we apply a negative bias at the back gate. And this back gate region is being used as a storage region. Now when you apply a negative bias, we can see that under gate 2, the energy level shift upward, and they shift in such a way that the electrons from this gate 2 region can tunnel towards the drain region. The shifting of electrons or the tunneling of electron towards drain results into generation of holes in this storage region, and the holes are increased to around 10 to the power 19. Thus, storage of excess holes defines state 1. Now talking about state 0, it intends to remove the holes from this storage region. For this purpose, we give a positive voltage at the back gate that lowers this energy level in such a way that the holes present in this region recombines towards the drain region, and our hole concentration decreases to around 10 to the power 6. So we can see that presence of excess holes defines state 1, while its absence defines state 0. Next important thing is, for how long can we retain this state? And that's defined by hold operation. So when you see that initially you have, this is the whole concentration, where we can see that it's around, the whole concentration here is around 10 to the power 13 in state 0, while in state 1, it's around 10 to the power 19. When you are increasing the hold time, with time, the holes are gradually generated in state 0, which degrades state 0, while a negative bias being applied at the back gate maintains this state 1. There will be a time when state 1 and state 0 cannot be distinguishable. Until that time, we can just hold this operation of state 1 and state 0, which is defined as retention time. Higher the retention time, better is the dynamic memory or its storage capacity. Next, how can we distinguish the state 1 and state 0 during the read operation? Now, during read 1 operation, a positive bias is applied at gate 1. This results into, because it's a P plus region and this is an intrinsic region, it results into electron tunneling towards the channel region. This electron is further drifted towards the drain by applying the positive bias at gate 2 and drain. Now, during read 1, we see that the whole concentration is higher always in state 1 and it's around 10 to the power 18, while in case of state 0, it's around 10 to the power 13. Now, presence of this higher whole concentration results into an effective higher potential in case of state 1. Therefore, it shows a lower barrier for the electrons in case of state 1 when compared with state 0. This is very clearly visible through this diagram where black shows a lower barrier for electrons and blue shows a higher barrier. So we obtain a higher read current for state 1 as compared to state 0. And the difference between this read currents is known as sense margin. So once we have understood how this dynamic memory operates, the basic functionality we can define is it depends upon regulating the whole generation and recombination in the storage region, which primarily depends upon the device architecture device. And in this case, I have designed 3 different architectures, which has their own specific requirements based on the DRAM matrices. And however, in each of the cases, the gate 1 is used to control the read mechanism, which is based on band-to-band tunneling, while gate 2 is utilized to create and maintain the potential well for the charge storage. Apart from this, other important factors that govern this whole generation and recombination are device dimensions, the bias applied, and the temperature. So next we'll see that how do we create and maintain this potential well, or how was this design proposed? So first thing is impact of backgate position. These are different cases in which the backgate alignment is really important. Now in case A, we see the front gate and the back gate are totally aligned to each other and we see that no potential well is being formed. Next, when backgate is completely aligned towards the channel region, we see a potential region which has a depth of around 0.5 volt, while in a misaligned case, we see 0.8. The next, we see 0.5 volt. And again, in a backgate extended towards drain, we could see a 0.8 volt of depth. So deeper the potential, higher is the retention time. That's what we can see here. In case C and E, where you have a deep potential well of 0.8 volt, we could see a retention time high, which is as high as 170 milliseconds. However, we opt to choose case C because it utilizes a lower drain voltage while write mechanism. Next important factor that governs the formation of potential well is its work function. Now, in case of gate 2, when we vary the potential, so N plus poly is around 4.2 electrovolts, mid gap it's 4.5, and P plus poly we have a 5.2 electrovolt of work function. So higher work function basically results into a deeper potential well, which helps us to sustain the charges for a longer duration. So apart from position of the backgate and the work function, the third important thing is the bias being applied. Now we have seen that for retention time, it's important that we could sustain state 1 and state 0 both for a longer time, but the bias applied is always the same. So in case of state 1, if we give more positive bias, we can see here the whole is recombined and the whole concentration decreases. So it degrades state 1. So therefore, due to whole recombination, we see state 1 degradation. But if we apply more negative bias, we can see that whole starts generating in the storage region that degrades state 0. So it's very essential to even apply an optimal gate bias. Next, I'll just show that I started with an ultra-thin box, which showed retention time in few milliseconds by optimizing the work function, the bias, and the backgate position, and having finally a double gate misaligned structure, the retention time was improved to 2 seconds at 85 degrees Celsius. Now, the impact of scaling this is when we scale down the storage region or the gate 2, we could see that there is a reduced storage area. So the retention time of the memory reduces. While if I reduce gate 1, which is responsible for band-to-band tunneling and read mechanisms, we observe a narrower barrier that results into reduced gate controllability and hence decreased sense margin. So the maximum scalability that could be attained by this device architecture was just 100 nanometer, and still we required further optimization. So just talking apart from sense margin and retention time that we have already seen, there are various other factors that are very important for DRAM performance, that is like scalability that defines the density of this. Sense margin is the difference between the current, while current ratio defines the ratio of I1 is to I0, and both of them are really important to have a better read sensitivity. Apart from this, the speed of the device, which is estimated through write time. Lower the write time, better is the speed of the device. And next is the power, which is determined by the bias applied. So to improve all these factors, I came up to a design that was basically the best, that was a planar Trigate. So the intention of having 2 gates at this tunneling region was because the double gate transistor showed sense margin in few nanoamperes. So there was a need to improve this gate controllability. And so we had a double gate which was electrostatically coupled. Now, apart from the backgate bias work function, we could see that this region, basically the gate 1 creates a virtual end region, while the gate 2 creates a virtual P region. And thus we have 3 junction which needs to be controlled in a very proper way to operate it as dynamic memory. As we see that write 1 operation is based on controlling the junction 3, the hold operation is based on controlling the junction 2 as well as junction 3, while the read mechanism, which is based on 3 different operations of band-to-band tunneling, diffusion, and drifting the electrons, is based on all the 3 junctions, that is junction 1, junction 2, and junction 3. And we observe that junction 1 can be controlled by optimizing the film thickness, work function of gate 1, and the bias applied at gate 1, while junction 2, which defines this barrier, it can be controlled through the film thickness through work function of gate 1 as well as gate 2, and the bias applied at gate 3. And next is the junction 3, which is controlled by film thickness, work function of gate 2, and drain bias being applied. So for design optimization, understanding each of these physical characteristics and optimizing this device dimension is very essential to have a high performance dynamic memory. Finally, achieving through all this, we could attain retention time of around few seconds at 85 degrees Celsius. The device could be scaled down totally to 115 nanometer. The speed could be reduced to 5 nanoseconds. The sense margin observed was in microamperes, while the device could operate at a low drain bias of 0.9 volt. Although the performance was better than the previous proposed device architecture, but still there was a need to improve device scalability. And that could be possible through optimal material device co-design. However, I couldn't work on this material design, which I wanted and which I have continued to work upon in my postdoc. So after this, I'll talk about my postdoctoral research. So I started my postdoc at UT Austin. So initially I did work on Monte Carlo modeling, but nowadays, so now I'm working towards DFT study of 2D material, and the intent of working on this device is to find the electronic properties and understand the transport mechanisms for few devices. One of my focus is to work on tunnel fed devices. So now when we talk about 2D materials, the 2D material are atomistically very thin material. So the advantage of having this thin material when talked in terms of tunnel fed is this: having an ultra thin body helps reduces the tunnel depth or the distance between this region, as we can see in this figure. So 2D material are a very good material for this. Second, it provides a better controllability. We can tune these devices very efficiently. There are various 2D materials available from which we can select according to the application required, and they provide flexibility. Now, we have utilized vertical stacking. So in 2D materials, vertical stacking utilizes van der Waals forces, which are important, and vertical stacking is helpful as compared to lateral heterostructure because it reduces the traps. So now in case of lateral heterostructure, you have the traps between this material system, and that degrades your off current. But having it vertically stacked eliminates this problem. And so I have studied various material system, their heterostructure, stacking the monolayers of them and understanding their electronic properties. So this electronic properties I've studied first through understanding the band alignment in them. So why do we need to understand the band alignment in 2D heterostructures is because they define the applications. So there are three different types of heterostructures that we know. First is type 1 heterostructure. So when you stack two 2D materials in such a way that the conduction band and the valence band are contributed by the same material or are localized in the same material, then it's a type 1 heterostructure. For type 2, we can observe that the conduction band is contributed by material A, while the valence band is contributed by material B, and it creates a type 2 heterostructure. While in case of type 3, it is a type of type 2 heterostructure, but the conduction band and the valence band overlap. So typically a type 1 heterostructure is utilized for light emitting devices. A type 2 is mainly utilized as photodetector, solar cell, memory devices, while type 3 is classically used for tunneling transistor. Next, moving to of my work. So I started to study DFT simulation on through a black phosphorus and MOS2 heterostructure. So in this figure, we can see that the black phosphorus is at the bottom layer and a MOS2 layer lies above it. Now observing its band alignment, we can see that the red is being associated with MOS2, and so we observe that the conduction band minima is contributed by MOS2, while the blue denotes for black phosphorus, and valence band maxima is localized to black phosphorus. So in this case, we see a type 2 heterostructure. Now this type 2 heterostructure, we can actually see the capability of the device by seeing how well it can be tuned. If a device has a capability to tune itself to a type 1 and as a type 3 also from type 2, it can be used for wider application. So to understand few of the things, I tuned it, and the first factor that utilized was electric field. Now you can observe here the 3-band alignment, where in the first band alignment, a negative electric field is being applied. So negative electric field is the direction is from the black phosphorus towards MOS2. So you have a positive bias being applied at black phosphorus. A positive bias at black phosphorus lowers its energy levels, while a negative bias as MOS2 upshift its energy level. And thus we can see that the band gap increases as compared to that at a 0 volt condition or at a no volt condition. So here, as we progress towards a more negative electric field, we could observe that at an electric field of around minus 0.6 volt per Armstrong, the heterostructure could transit from type 2 to a type 1 heterostructure. Next, showing that when we apply a positive electric field, so positive electric field direction is from MOS2 towards the black phosphorus. So again, we can observe that by applying a positive voltage at MOS2, its energy level decreases or lowers down, while a negative voltage at black phosphorus upshifts its energy level. Therefore, the band gap of this heterostructure decreases, and further moving towards more positive electric field, we could observe that at an electric field of around 0.7 volt per Armstrong, the band alignment turned into type 3 heterostructure. Apart from electric field, material engineering is an important factor where we could replace few of the material system to form different type of architecture. Now, first we studied the band alignment of monolayer. These are all isolated layers and it's not in heterostructure, but just looking at this monolayers, we can see here also the type of alignment could be predicted. So if we see a black phosphorus and MOS2, we can see here conduction band contributed by MOS2, by valence band contributed by black phosphorus, which shows a type 2 heterostructure. Similarly, if I see for molybdenum diselenide, I can see the conduction band is also contributed by black phosphorus, by valence band also by black phosphorus. So it's a type 1 heterostructure. And coming towards hafnium diselenide, we can see the conduction band being contributed by hafnium diselenide and valence band by black phosphorus. And there is an overlap between the valence band and the conduction band. So just by analyzing the isolated monolayers also, we can understand the type of alignment. However, these are the actual alignments that we have when we stack both the heterostructure. And I could observe that black phosphorus MOS2, while it shows a type 2 heterostructure, the other TMD materials when stacked with black phosphorus could show even a type 1 and a type 3 heterostructure. So the choice of material system for your application is important and seeing their band alignment. Next, other factors that could affect the band tunability is one of them is strain engineering. So when you strain a heterostructure material, you affect their atomic orbitals, the atom overlapping, those are being affected. And this changes the energy level of each of the material system. And by doing this for a black phosphorus and MOS2 heterostructure, by applying a comprehensive biaxial strain of around -5%, we could observe the band was tuned down to a type 1 heterostructure. Now, we have already studied that how through electric field, by applying a negative electric field, it can be tuned to a type 1, while applying a positive electric field, it can be tuned to a type 3 heterostructure. Other possible thing is by layer engineering. Now, black phosphorus is quite flexible and is very tunable. So while having more number of layers for black phosphorus, we can reduce the band gap. And also we could observe that when a MOS2 layer is stacked with 4 layers of black phosphorus, it can be tuned to a type 1 heterostructure. And next is material engineering, that definitely describes that how we can tune the band. So right now I'm studying about this band alignment, but the purpose of this work is to design the FET that can operate for low power application, and for which I'll be studying some transport models of this. Next, I'll share a few of my thoughts based on the learnings that I had from my PhD as well as postdoc. So I guess PhD is the time when you get to explore a lot. So if you get an opportunity in terms of mentoring a person, teaching a person, writing a proposal, it's always a good learning experience, and I think we should always grab it. Secondly, conferences are really a nice way to improve yourself in terms of your communication skills, in terms of interacting with others, networking, and it also gives you a wider perspective about your work. A few other things that I think is like a habit of penning down, that I believe just penning down your ideas are helpful, because you never know at that point it may sound like it's not important, but going back it can help you to further think upon that. Next, so PhD, you have lots of ups and downs, but it's good to have mentor, your friends, family whom you can talk to. It's important also to stay motivated with your professional goals, and you must be able to change yourself from the environment if it's not helping you to work or something. That can be done by new place, having a new hobby. Also, it's important to motivate yourself. It's not easy to self-motivate, but it's really good. So few of the things that may sound stupid, but I like doing it, is like I keep aside few of my achievements or a few of the reviews that I get in my journal, which appreciate my work. So reading them give me a kind of self-confidence to work. And next, I think the most important thing is your relationship with your advisor. The healthier the relationship you have, the better it is for your learning. So if your ideas with your supervisor even doesn't match, I think it's important to communicate and try to share your thoughts now and then wherever you feel possible. Secondly, also have a helping and a healthier relation with your lab mates, because you are all traveling in the same boat, so it's good to learn from each other experiences. And also it could be helpful from the point of view of collaborating sometime in future. So I think that's from my end. Thank you. Thank you for hearing me.
Can you hear me? I always have this. Can you guys hear me?
Yeah.
I had a question on your like HBN MOS2, right? So what software do you use for those calculations?
I use VAST.
I see. How do you create the unit cells for these 2D?
The unit cell for 2D materials. So there are lattice mismatch between them. So we take the supercell of this 2D materials so that it can have the lattice match between them. So
how many atoms in a unit cell? Because they're not any more crystalline. They're not like 3D, right?
yes. So in this case, in this supercell, there are 44 atoms in one single unit cell.
That's a lot of atoms.
Yeah, that's not. But to have a lower lattice mismatch, it's required to have that.
I see. Okay. Yeah, great talk. Thank you.
Okay, thank you.
I have a question. I'm curious about, you said you were a professor, assistant professor for a time. I was wondering about that experience. So, how did you come across it? Did you learn anything from it?
So I just wanted to continue something in my field, so I opted for it. It was really a very nice experience, and that was something that pushed me towards PhD. So I started enjoying teaching. It was good to work with students. And so I thought that I want to have my career in academics. And so that's how there has been a step for, going first for the PhD and then going for a postdoc, so that finally I could end up into an academic field.
I see. That's really cool and kind of unusual. Yeah.
Thank you.
So you did your PhD and then you continued like your PhD work into your postdoc?
It's not continuation, but I did wanted to work on the material perspective. So I got an opportunity to work here. Obviously, I want to combine that work. That's my future goal, to combine my PhD and the postdoc work, have a material device kind of co-integration. So yes, but right now I'm just working upon the material perspective.
What do you like? You want to go more into academia as a future?
Yes, yes.
That's nice.
Any other questions?
Is there a reason like when you went to postdocs, like how did you choose this group? Like what were the reasons like for you to choose a particular group? Like I know you did your PhD in India, right? And then you had probably had different places that you wanted to go. I know you said you want to go academia, right?
Yes, that's correct. That's correct. So I guess one of the factors that I came here is personal reason. Also, I got married and my spouse was in Austin. So it was best for me to look something in UT Austin. And I mean, coincidentally, I got and I was lucky enough to get into the research group that works on nanoelectronics, and the kind of work that I am doing exactly similar. So that's how it worked for me.
You had Austin and then you put it around Austin. I see.
Yes, I wanted to have that, both the balance of the personal and professional life, and so I chose it.
How do you think your PhD is different? Like, what is the stress level as in a PhD and the stress level as in a postdoc? How is your two lives different?
Oh, I feel that my PhD was more relaxed as compared to a postdoc, because PhD, you're not in a pressure or a timeline. It is there, but still it's not that strict. As a postdoc, you are like you're neither a student, a PhD or graduate student, nor you're a professor. So going into that, you're running for that professorship or going into academics, it's really tough. And you're expected, like in a postdoc, you're really expected to have papers from initial, because you already have that research experience.
Mm-hmm.
So individually, for me, it's the postdoc that's more stressing as compared to PhD. PhD, I think it only becomes more stressful for you when it's the timeline or the work that you're not able to do. But I think it took me time initially just to get a first result of me. I remember I took 2.5 to 3 years, which was a long time. But soon after that, in the next 1 year, I could give a very nice result. So somehow I have that memories. And that's fine to have your PhD for 4 or 5 years, but postdoc, you really cannot say about that.
So did you have ups and downs? Like you said, you did masters and then you did what do you say? You went to teaching, right? And that's why you're like, oh, I want to go to academia. But
Yes.
did you had any doubts like, hey, maybe this is not for me? And if so, how did you overcome it? Like, I usually have those doubts. Like my initial years, I'm like, oh, I want to go to academia, but now I'm just like, no. This is too much of stress, How did you like overcome all this and you're still like, hey, I still want to go to academia? What's that drive for you?
I think the most one thing is I like teaching, and I feel that I want to learn more and more in this field. That's the urge that makes me feel like academic will be good. So I have that motivation in me. And as I told you, I don't want to forget it. So sometimes it does happen that I do write few things and I try to read them when I'm getting demotivated, so that I don't forget my, the end goal. Yeah, it does help me, although it's a little stupid, but yeah, it helps me.
I have a recording, so I will probably put it in our website for people who couldn't attend today. And there are people from like other universities like Texas State that were trying to do events together. So they did want our recordings too. So I'll send it to them as well. Yeah, it was really nice to listen to what you had, Nupur. Yeah, thank you.
Great talk, Nupur. Great talk.
Nupur.
Thank you.
Thank you. Bye-bye.
Bye.
Bye.